One thing that rock and roll and math have in common is that they both make our bodies shake. The difference is that while some shake for rock and roll out of passion, others, maybe most of us, shake for math out of a deep-seated fear of failure. Math is a frightening word for many people. But I discovered something that will bend, turn inside out, stretch, and transform the way you think about it. One evening, I was reading a web article about the loop quantum gravity theory for fun. Oh yes, I am a nerd. And I found the word topology in it. A word that was completely foreign to me, so I asked my very smart friend about it. In other words, I Googled it and got an answer. Topology is the study of geometric properties and spatial relations unaffected by the continuous change of shape or size of figures. What? I thought, this sounds crazy. I need to study this badly. And so I did my studying and research, and I realized that all math I learned is a foundation for something truly beautiful. Something that can describe so many things in the world. I called that the real math. And now, I'm about to introduce you to something unbelievable. I'll tell you this and blow your mind. You are all donuts. Some of you have sprinkles. Some of you are rainbow donuts. Some of you are glazed donuts. Some of you are double, triple, or even quadruple donuts, but you are all donuts. And I will walk you through and prove that to you. But first, before we start groaning, just hear me out. What happens if we apply math that we learned to something beyond the boundaries of the school math classes? The result will surprise you. I can confidently say that you will be able to turn any object into almost any other one, just like that. Snap, and you turn a pair of glasses into a pretzel. Snap, and you turn a coffee mug into an elephant. Wait. Oh, snap. Oh, here we go. But first, let's get familiar with the game, right? But what's the game? The game is understanding the nature of objects around me. So what are its rules? Any object that you create has to be made of an extremely stretchable material that can bend, shrink, and ripple as much as you wish. But you cannot join, rip, or make holes in the material. A good example of such a material is plastic wrap or latex. Let's take a rubber balloon and squish its sides. We change its shape, but when we do so, it's still a spherical balloon. So the shape isn't constant, but the object is constant. This means that objects do not need to have exactly the same shape in order to be the same. But what makes us conclude that some things are the same while other things are different? This time, imagine a gigantic sphere made of Play-Doh. Now, try to mold that sphere into a donut. Take your time. What you might try considering is probably stretching your sphere into a thin sausage and then bringing those ends closer and closer together, but you cannot join the surface. That's against the rules of the material, so that method doesn't work. All right, let's try another one. Let's take our sphere, squish it from top and bottom, and then make a hole in it. But we will be making the hole in the material, so that is also not allowed. Actually, I gave you a task that it is impossible to complete, but I appreciate your effort a lot. The reason why none of those methods work is because a sphere and a donut are truly fundamentally different objects. They have a different number of holes. Such fundamental properties do not only show us differences between things, but they also help us find similarities between something that we might have considered different. Who would think that humans and donuts are similar? However gross this may be, humans have one metabolic tract, which is simply a long hole. The rest of the curves do not matter because we can easily even them out. So after all those transformations, we end up as donuts. In the same way, glasses and pretzels both have two holes, and coffee mugs and elephants both have one hole. So even though the shape is different, intrinsically, they're the same object. The wonders do not end here. The next step for us is to find out if the fundamental properties of objects are the same. Does that count for lines as well? Well, it does. And the first thing that we're going to do is we're going to take a look at the first thing that we'll learn in our math classes, parallel lines. Since middle school, our math teachers taught us that if we have one line, we can draw another one parallel to it pretty easily. Do you think that is always the case? Well, there are two answers to that, a short one and a long one. The short one is no. The long one is, well, it is more complicated. If we take a look at the sphere, we notice that all its lines go around the sphere where its width is the greatest, just like longitudes do on the globe. And if we try to draw any such two lines on the surface of the sphere, they will always intersect, which means that it is impossible to have parallel lines on the surface of a sphere. A fun fact, if you ever try to draw a triangle on the surface of a sphere, hoping to find that the sum of its angles, well, famously known as 180 degrees, you will be frustrated because the sum of its angles will be greater than 180 degrees. Now you know why the Bermuda Triangle is considered paranormal on Earth. So, is geometry limited to a flat plane? Amazingly, not at all. You want to draw a square on the surface of a donut? Sure, and that square will follow the rules of a donut geometry. You want to draw a triangle on the surface of hyperbolic pans? Oh yes, pans, that's an actual name for this design, I'm not kidding. Go ahead. And that triangle will follow the geometry of hyperbolic pans. Anything, from a light bulb to your pet gecko, has its unique geometry. Have you ever wondered why, when a plane travels across the Earth, it follows a curved path? The reason is, the shape of the Earth is basically a sphere. The distance between any two lines is a line segment, and all lines on the sphere are curved, so the path that you follow is curved too. And there exist geometries for even the most irregular shapes too. The shrunken ends of lattice leaves and the surfaces of corals have a hyperbolic geometry. While on the flat plane, there can be only one line parallel to another, passing through one point, and on the sphere, there are no parallel lines at all. Isn't that sad? However, on a hyperbolic surface, oh yeah, that's an example of a hyperbolic surface, there can be infinitely many lines passing through a single point and being parallel to a single line. Hyperbolic geometry is used in astronomy for describing the structure of the universe. Also, According to modern physics, the reason why we have gravity is because space and time themselves are not flat. They actually curve under high masses, so space-time has its own geometry too. Our world is so rich with all these remarkable geometries that we deal with every second of our lives. And yet here we are, stuck with 180-degree triangles. By the way, everything I've just told you is based on the math that we already know. Yet I doubt that somebody in the audience would find me showing you a formula entertaining. Every math teacher can confess that at least once during his or her career, a student asked, "Why are we studying this? How is this related to real life?" We're used to thinking that math is just lifeless x's and y's and faceless numbers and algorithms. Is that the math that we will use in our daily life? No, this isn't the real math. The real math is the meaning behind these equations, not the calculations themselves. The real math is the patterns that we observe in the world around us, and it's the reasoning that we use to find those patterns. Introduction of high-level topics and implementations of math in real life and scientific discoveries can make math more exciting. The curriculum doesn't need to teach advanced concepts, but understanding there's something much more is a start towards the real math. What is more beautiful than this? Embrace the beauty of mathematics. And remember, you are a donut.